Hi guys, I hope you are ready for your final YouTube video for College Trig. Today we are going to go ahead and look at section 6.5 and look at the trig form of a complex number. Now a complex number is not a new idea for you. We studied these in Algebra 2 as well as college algebra. A complex number is in the form a plus bi or a minus bi. Remember, what makes it complex is that you have a real part followed by an imaginary part, and you are either adding or subtracting. So let's just go ahead and do some brief review first. Recall from college algebra that you can represent a complex number, we're going to call it z, as a plus bi on what's called a complex plane. So that's the first space, a complex plane. Now, because the complex plane has the real axis side to side, so the horizontal axis is the real axis, and that's the first value that they give you in a complex number. So it is a. Your real number will tell you left or right. The vertical axis is the imaginary axis, and that is the second value. So the second value tells you up or down. And so what we talked about in college algebra is even though your number is written in the form a plus bi, or it's even a little bit easier to see here, you can represent that number as an ordered pair because the first value tells you if you go left or right. The second value tells you if you go up or down, just like a normal coordinate plane or an ordered pair would when you're looking at the coordinate plane. You just have to realize that side to side is your real number, up and down is imaginary. So let's go ahead and graph some complex numbers. So the real number is -1, the imaginary number is 3. So you go to the left, 1, up 3, and that's -1 plus 3i. My real value is 5. My imaginary number is -2, so I go to the right 5 and down 2, and this is 5 minus 2i. Kind of fun. The real number is 8, the imaginary number is 5, so you go to the right 8, up 1, 2, 3, 4, 5. Here is your point on what's called the complex plane. This point represents 8 plus 5i. Next one, the real value is -2. The imaginary number is -6. So to the left 2, down 6, this is -2 minus 6i. Now the next one, I just have a 7i. So that means your real number is 0. Your imaginary number is 7. So your point will land on the imaginary axis because you're not going left or right. So I stay at 0, go up 7. That's the location for 7i. This can also be shown as an ordered pair. The real number is -10. There is not an imaginary number, so you'd put a 0. So I go to the left, 0. I do not go up or down. So again, this was a skill that we did in college algebra, but what we're looking at today is based off of this kind of idea. Another thing that is review, okay, the absolute value of a complex number. Remember, absolute value, what it means is the distance. So if you take the absolute value of a complex number, what you're doing is finding the distance between the origin, which is 0, 0, and your point on the complex plane. This was the formula that we used in order to find the absolute value. You take your real value and square it, plus your imaginary value and square it. Notice you do not have the I in here. The I just helps you figure out what that imaginary value is. So here's an example of what that would look like. If they wanted you to plot 3, 6, this is positive, so you go right 3, up 6. So that's where the point is. If you wanted to find the absolute value, you take the real value, which is 3, square it, plus the imaginary value, which is 6, and square it. 3 squared is 9, 6 squared is 36, 9 plus 36 is 45. This is not a perfect square root, so you simplify it if you can. Let's go ahead and try another one. If I want to graph -2, 5, remember the first value would indicate for us that we go to the left 2. The second value is going up or down. It's a positive 5, so I'd go up 5. So left 2, up 5. When you find the absolute value, what you are finding is the distance from this point to this point. So to find the absolute value, you take the square root, the real number, -2 squared, plus the imaginary number, which is 5 squared. -2 squared is 4. 5 squared is 25. 4 plus 25 is 29. I cannot break it down, so that is the absolute value. Okay, so again, those are values, or those are just review concepts that we looked at in college algebra. Now we're going to go ahead and move on to what they call the trig form. This, again, is going to be based a lot off of that unit circle, and that's hopefully something that you saw throughout this course. The unit circle is very important. So again, that idea will come back for the rest of the notes for today. So in college algebra and in algebra 2, we talked about adding, subtracting, multiplying, and dividing complex numbers. Okay, those are skills that we work through. In order to effectively work with powers and roots of complex numbers, oftentimes it's helpful to write the complex numbers in what's called a trig form. Okay, so in this picture right here, what happened is they are now visualizing this point as being a point on an angle. It's the point on the terminal side of an angle in standard position. So what they're saying is if you have your initial point, so again, thinking back to that unit circle in that form, you would go ahead and have your vertex at the origin. You're looking at the positive real axis. You're measuring counterclockwise to the terminal side that contains your complex point. This angle is theta. What they want you to realize is that you can write this, your real number is r, where r is the distance from 0, 0 to that point. It's the same formula. You take the real value, square it, plus the imaginary value, square it, take the square root. That's what r is. A is the real value. It comes first. So you're going to take the x value, which is the cosine. Remember, it's in your unit circle. It's cosine and sine. So this is the x, this is the y. This comes first, this comes second. So they are saying that a, when you're thinking a plus bi, if you're writing it in trig form, you are taking r, this value, times the cosine of this angle, plus r times the sine of this angle, and that part is imaginary. So this is kind of how they wrote it out for you. A plus bi is r times the cosine of theta plus r times the sine of theta I. And you can obtain this from any complex number. Again, we will use the help from the unit circle. Now, if I want to find out what this angle is, the tangent of theta equals b over a, just like we have been looking at with vectors, you guys. So you would go ahead and take the b value divided by the a value, find out where on the unit circle the tangent is that, and then you would know your theta. So let's go ahead and do some of this. I know it might seem a little confusing, but once you do the examples, I think you're going to be like, holy smokes, that's it. One thing that they have us do, on one page in your book, they're like, hey, let's write it like this. A plus bi equals, they kept the r with the cosine of theta plus r times the sine of theta I. Then on the very next page, and so you'll see that in the notes, they're like, guess what? This is like a greatest common factor. So you really only have to write r, which has a fancy name. Now they're calling it the modulus. So r is still the same thing. The real value squared plus the imaginary value squared, you take the square root. That is the modulus. Because it was going to both the cosine and the sine, they're saying, okay, save yourself some time and just write it out front of both of them. So it's like you're dividing out the greatest common factor. Then the argument. The argument is what they call theta. So it's the cosine of the argument plus the imaginary sine of the argument. So again, just building that mathematical vocab. When they talk about an argument, it is theta in the trig form of a complex number. When they talk about the modulus, it is the value of r in the trig form of a complex number. Now more vocab. The trig form of a complex number is also referred to as the polar form. Okay, and so as you go further in math, you might learn something like polar coordinates, that sort of thing. This is kind of the introduction. So this could be called the trig form of a complex number, or simply just call it the polar form. It's getting you ready to transition into what are called polar coordinates. Because there are infinite amount of choices for theta, because you guys, we're going back to our friend the unit circle. Remember, you can go around and around and around as many times as you want. Well, when that happens, that means you have an infinite amount of solutions. So rather than having an infinite amount of solutions, they are restricting your domain. You have to just go from 0 to 2 pi, meaning you need to stay within the unit circle, okay? If they give you a complex number, can you write it in trig form? Sure we can, because we are rock stars. Okay, so the first thing you want to do is find your modulus. You take the square root. The real value is -2 squared, plus the imaginary value. What's attached to the I? -2 square roots of 3. Okay, so it's the real value squared plus the imaginary value squared underneath the radical. -2 squared is 4, plus this exponent has to go to both the -2 and the square root of 3. -2 squared is 4 times, now if I square the square root, this is going to cancel, but remember it never changes whatever's underneath the radical symbol. So this does stay a 3. Order of operations, you would multiply before you add. So 4 times 3 is 12. 12 plus 4 is 16. Square root of 16 is 4. So R is 4. Now what we need to do, you guys, is figure out what our argument is. The tangent of theta is b over a. And here it's going to be very important to figure out what quadrant we are looking in. So remember, the first value, your real value, is the cosine. So the cosine is negative. The second value, the imaginary value, is the sine. The sine is negative. So in the unit circle, negative cosine means you go to the left. Negative sine means you travel downwards. So if I go to the left and down, we are looking for our argument to be in quadrant 3. Now to figure out what our value should be, we take b, -2 square roots of 3 over a, -2. So it's the imaginary value over the real value. Negative cancels, 2 cancels. So what we need to do is figure out where in quadrant 3 is the tangent. And remember, in the unit circle, tangent is y over x. Where is the tangent equal to the square root of 3? So if I go ahead and I look at the unit circle, I have to stay within quadrant 3 because that's where the sine and the cosine are both negative. I do see a couple different options where I have a square root. Sometimes you might have to try a couple. Let's go ahead and try 4 square root of 3. If it doesn't work, then we can try 7 square root of 7. Or sorry, 7 square root of 6. If I try 4 square root of 3, the ordered pair is -1/2 and negative square root of 3 over 2. Now we want to see if the tangent equals a square root of 3. The tangent is the y value, so negative square root of 3 over 2, divided by the x value, which is the same as multiplying by the reciprocal. So this would be -2 over 1. Negative cancels a negative, 2 cancels 2. What I end up with is the square root of 3 over 1. So this is my argument. This is my modulus. Now all we have to do is write the number in that trig form. So the modulus goes out front. Then it's the cosine of 4 pi over 3 plus I, the sine of 4 pi over 3. That is the polar form and you're done. So you have to find the modulus using the formula. You have to find the argument using the unit circle, knowing which quadrant to look in, making sure that you can have the tangent match whatever b divided by a is. Let's do another one, just in case you're like, oh my gosh, what just happened? Okay, to find the modulus, underneath the square root, you take the real number, in this case it's the square root of 3, and you square it, plus the imaginary value, in this case it's a 1, and square it. When you square a square root, the square root cancels, but it does not change what's underneath. So this is a 3, plus 1 squared is a 1. 3 plus 1 is 4, and the square root of 4 is 2. So the modulus is a 2. Now I need to go ahead and figure out the argument. The tangent of theta is b, 1, over a square root of 3. But before I look, you have to figure out what quadrant it's in. Your real value, the first value is the cosine. The cosine is positive. Your imaginary value is the sine. The sine is also positive. Going to the right, if your cosine is positive, going upwards if your sine is positive. So if I go to the right and up, I am looking in quadrant 1. So I need to find a place in quadrant 1 where y divided by x is 1 over the square root of 3. So again, I'm just looking here. Obviously, I need to use one of the order pairs that contains a square root of 3. And I'll be honest, you guys, 9 times out of 10, I pick one and it's the wrong one and I have to get the other one, okay? To make the video not so long, yes, I worked through them ahead of time, and I guarantee you I picked the wrong one. But the answer is pi over 6, and I'm gonna show you why, okay? So your argument, if I look at pi over 6, it's the square root of 3 over 2 and 1/2. If I am finding the tangent, it's the y value, 1/2. Times the reciprocal of the x value, which is 2 over the square root of 3. The 2's cross cancel, 1 over the square root of 3, and that's what I need. So my argument is pi over 6. My modulus, sorry, weird word, is a 2. So now I can go ahead and write this in what's called polar form. The modulus goes out front. Then it's the cosine of the argument, so cosine of pi over 6, plus I times the sine of the argument. So the sine of pi over 6, and that's it. So these two examples show you how you can go from a complex number, like we looked at back in algebra or college algebra, and turn it into the trig form, also known as the polar form, using the unit circle and the formula that they gave us for the modulus. Super cool. Okay, now we're gonna go ahead and go backwards. If they give you the polar or the trig form, could you figure out what that complex number would be? Okay, first off, this is a no-no. The square root of 8, you can simplify that because 8 is 2 times 4 and 4 is 2 times 2. I can cross off 2 2's, so this is really 2 square roots of 2 outside of the cosine of negative pi over 3 plus I times the sine of negative pi over 3. You got to make sure, even like as you're looking through the book examples, at this point, you guys, they're going to start doing this on purpose to try to throw you. These little skills, they're just assuming that you would catch that. So I did want to make sure that we did that one together. Okay, now you need the unit circle. Negative pi over 3. What that means, remember the bottom is a 3, so that means you're looking at half of the unit circle. So you're going ahead and dividing it into 3 sections. Could not spit that out. Okay, so it's negative, so here is 1/3, here is 2/3, here is 3/3. And remember, it continues, so whatever the denominator is, that's how many sections you have. This is saying that we're going negative pi over 3. Yes, you're going to be looking for the denominator, that's a 3, because if I go negative pi over 3, 1 more pi over 3 would be 6 pi over 3, which would be 2 pi. So when they say negative pi over 3, it's actually 5 pi over 3 from the unit circle. Okay, negative just means you travel downwards. So I'm going to go ahead and rewrite that because when you look at a unit circle, they don't show you the negative values. Negative just means that you traveled in the downward or negative position. Negative 5 pi over 3 is, or sorry, negative pi over 3 is equivalent to 5 pi over 3. I'm struggling tonight, you guys. I've done like 36 plus hours of YouTube videos, and this is my last one. Crazy. Okay, here we go. Now you're going to use your unit circle because the cosine of 5 pi over 3, you guys, that's the x. The sine of 5 pi over 3, that's the y. So I have 2 square roots of 2 outside of, yay, unit circle. The cosine of 5 pi over 3, 1/2. Plus an imaginary. The sine of 5 pi over 3 is negative square root of 3 over 2. Last step, you guys, you just have to distribute your modulus. So if I bring this in, okay, top times top, bottom times bottom, this is technically over a 1. So I'd have 2 square roots of 2 over 2. Now this is positive times a negative, so I'm going to go ahead and realize positive times a negative, that's going to be a negative. Imaginary. When you're multiplying this, remember this is technically, there's a 1 underneath. Top times top. Outside numbers get multiplied, so it's a 2 on the outside. Inside, 2 times 3 is 6. The bottom, 1 times 2 is 2. So again, remembering when you multiply radicals, inside goes with inside, outside goes with outside. Now we can just simplify. 2 cancels a 2. 2 cancels a 2. So we have square root of 2 minus square root of 6i. It is okay for the I to be in front of the square root of 6 or behind. Because we're going into complex form, we typically write the I in the back. For complex form, it's in the front for that polar form. But if you were to keep it out front, you're not losing any points. Okay, let's look at another one. The modulus is 2. The cosine of 120. So you go to your unit circle. 120 cosine is the x value. That is negative 1/2. Plus I, the sine of 120. The sine of 120 is the square root of 3 over 2. All you have to do now is distribute the modulus. 2 times a negative 1/2 is negative 1. Plus, okay, this is a plus. When you multiply this, I end up with 2 square roots of 3i over 2. I can go ahead and cross cancel those 2's. So you'd have negative 1 plus the square root of 3i, and you're done. All you're doing is using the unit circle to identify the value for the cosine and the sine of the argument. Then you distribute the modulus. That's it. One more time, and you guys, you are done with YouTube videos. Hopefully, when we start calculus next fall, we will be in the classroom, and you never have to listen to me on YouTube again. That is probably your wish more than my wish. I do miss you all so, so very much. Way to hang in there and finish strong. I'm very proud of you. Last question. Your modulus is a 4. I can't simplify that in any way. We're good to go. Cosine of 3 pi over 2. Well, 3 pi over 2 is right here. Your cosine, the x value, that's a 0. Plus I times the sine of 3 pi over 2. 3 pi over 2 is at 270 degrees. The sine is the y value. So if I multiply it by negative 1. Check this out, you guys. 0 plus I times a negative 1. Do you agree that could just be a negative I? Because 0, you don't have to show it. Positive I times negative 1 is a negative I. So now when I distribute that, you just have negative 4i and you are done. That is a complex number. Yes, if they wanted you to show the real part and the imaginary part, 0 minus 4i would be required. All they're doing is just having you write in standard form, meaning get rid of the sine and the cosine. Here is a suggested assignment. Tomorrow is Friday. It is your test for vectors and all of those super fun things that we did in chapter 6. You do not have to take a final for this class, as you probably have figured out already. I did talk to the college and just let them know with the time constraints and distance learning, we just did not get to it. So we did get the final exam excused. Here's the suggested assignment if you want to practice this last concept one more time. Tomorrow there will be a Zoom meeting from 9:30 to 10 to ask any questions you might have over chapter 6. Then you can have the rest of the day, go ahead, open book, open notes, take that final trig exam. It's just on chapter 6. It's not on the whole semester. Only chapter 6. And when you're done, Make sure all of your assignments from May 11th through May 22nd get into your packet, turn it into the school. Please also include your textbook and if you borrowed a calculator, because it's our last turn-in. Again, I'm very, very proud of you. I hope you enjoyed our time together through this distance learning, and let's all keep our fingers and toes crossed that we can start in the classroom for calculus next fall. Miss you all so much. Have an awesome summer.